In continuation of our lectures in polymer chemistry CHM 155, we will be discussing about free radical addition polymerization, chapter 6. But before we go into chapter 6, I will briefly remind us about what was covered in chapter 5, that is classifications of polymers. If you remember, we discussed about 6 main classifications of polymers, which include the origin, that is the source of the polymers. So polymers are classified based on the origin, and this classification is subdivided into 2: natural and synthetic polymers. Natural polymers are polymers that exist in nature. For example, natural rubber, cellulose, DNA, which are usually called polynucleotides, and then we have starch, which are called polysaccharides, and then we have proteins, which are usually called polyamides. Under synthetic polymers, these are polymers that are produced by industrial processes. An example of such polymers include polyethylene, polypropylene, polystyrene, polyvinyl alcohol, polyvinyl chloride, polyethylene terephthalate, polycarbonates. The second classification is based on thermal behavior, that is the behavior of the polymer when heated. And under these classifications, we have thermoplastics and thermosets. Thermoplastics are polymers that melt when heated. Just like a candle, when you heat a candle, it begins to melt. Any polymers that behave that way is called thermoplastics. An example of thermoplastics include polyethylene, polypropylene, polystyrene, polyvinyl chloride, and polyethylene terephthalate, nylon, etc. And the other subclassification is called thermosets. Thermosets are polymers that do not melt but decomposes when heated. It's just like when you apply fire on a paper, it does not melt, it decomposes. Polymers that behave that way are called thermosets. An example of that include phenolformaldehyde resins, unsaturated polyesters, melamine, polymer epoxy resins, and other epoxy-based systems. The next classification we discussed was the classification based on the structure of the polymer. And under this classification, we have linear polymers, branched polymers, and cross-linked polymer. And a typical example of this is polyethylene. We said we can have a linear polyethylene, and this linear polyethylene are called high-density polyethylene. Then we have a branched polyethylene, which I call low-density polyethylene, and then we have cross-linked polyethylene, which is usually called cross-linked polyethylene. All these polymers have the same structure, which is ethylene. They are all based on ethylene, but they have different properties. For example, polyethylene, high-density, low-density polyethylene is usually soft and flexible, and therefore they are used for packaging, and this is what you find in most of the supermarkets. The high-density polyethylene is relatively stronger than low-density polyethylene, and these are used for the packaging of soft drinks or Laban like Almarai. This container is made from high-density polyethylene. Also, the cap here is made from high-density polyethylene. Cross-linked polyethylene, because the polymer chains are connected together by a strong covalent bond, they tend to be very strong, and therefore they are used as an underground cables, as an insulator for underground cables. So if you look at this, these are all polyethylene, 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 but because of their structures, differences in their structures, they have different properties, and therefore they are classified differently. So we have the difference between low density and high density polyethylene is the branching. The low density has shorter branch. The low density has longer branch than the high density. The high density have a shorter branch. And you remember that density is equals to mass over volume. So if the mass is the same thing, the volume will determine the density. For example, if the branch is long, it means that it will occupy more space, and more space means what? Low density. So low volume, high density, high volume, low density. The next classification is based on composition. That is the type of monomers that are used to produce the polymer. And here we can have, if a polymer is made from one type of monomer, it is called homopolymer. If it is made from two types of polymer, it is called copolymer. And if it is made from three different types of monomer, it is called terpolymer. The copolymer also is divided into four, depending on the arrangement of the monomers. If in this case we can have what we call an alternate copolymer, random copolymer, block copolymer, and graft copolymer. If you are still confused with this terminology, you should please go back and read page 55, 51 of your course material. The next classification is based on crystallinity. Crystallinity is the arrangement of chain, and under this classification we have amorphous polymers, which contain irregular arrangement of chain, like a spaghetti, and we have crystalline polymers, which have a regular arrangement of chain, and of course we have semi-crystalline polymer, which has combination of regular and irregular arrangement of chain. For industrial polymers, there is no example of 100% crystalline polymers. But in the case of amorphous polymers, we have, for example, polystyrene, polyvinyl chloride, polycarbonate. All these polymers are transparent. And when you look at here, you see that the polymers that are transparent are usually what? Amorphous. These include polycarbonate, polymethyl methacrylate, which are used as contact lenses, or polycarbonate, which is used as headlight of our car. They are all what? Transparent. Semi-crystalline polymers are usually non-transparent. But of course, one advantage of polymer is you can make non-transparent polymer to become what? Transparent. For example, polyethylene terephthalate, by playing with the rate of cooling during processing. So here we have examples of semi-crystalline polymers, and here we have example of amorphous polymer, which are usually what? Transparent. The last classification that was discussed was based on polymerization reaction. That is reaction that is used to produce polymer. To simplify this reaction, we said some of the polymerization reactions involve a double bond, and some reactions involve functional group. So polymers that are addition polymers are polymers that are formed by reaction of double bond, while condensation polymers are polymers that are formed by the reaction of a functional group. So under polymerization reaction, we have two sub-classifications, which is addition polymers and condensation polymers. Chapter 6. In chapter 6, we'll be discussing about these classes of polymer, that is classification based on polymerization reaction. So generally, when we look at polymerization reaction, we define polymerization reaction in chapter 4 as a reaction in which monomers are chemically converted into a polymer. And this polymerization is divided into two, either condensation polymerization or addition polymerization. Condensation polymerization involves reaction of a functional group, And you remember in chapter 1 we talk about different types of functional group: alcohols, aldehyde, ketones, epoxies, and some other functional groups. Now, under addition polymerization is subdivided into three. This depends on the materials or the catalyst that is used during the polymerization. Now, if a free radical is used during the polymerization, then that is called free radical addition polymerization. If an ion is used, and this ion could be either cation or anion. If an anion is used, then it is called anionic polymerization. If a cation is used, it's called what? Cationic polymerization. These two polymerization processes are called ionic polymerization. Of course, the last one is coordination polymerization, which is based on the catalyst. And most of the industry, especially here in Saudi Arabia, SABIC and Tesne, most of the polyolefins are produced by coordination polymerization. And these polymerization techniques produces polymers that have different properties. So in chapter 6, we'll be discussing about addition polymerization. In chapter 7, we'll be discussing about ionic polymerization. And in chapter 8, we'll be discussing about condensation polymerization. Chapter 9, we'll be discussing about special type of polymerization, which include coordination polymerization and ring opening polymerization. So any polymerization that is initiated by a free radical are called free radical polymerization. If it is initiated or started by a cation, that is called cationic polymerization. And if the polymerization is initiated by an anion, then it is called what? Anionic polymerization. But if the polymerization is started or initiated by a catalyst, then it is called coordination polymerization. Now, another name for this addition polymerization is also called what? Chain growth. Chain growth, as I mentioned earlier, that this reaction involves monomers that have carbon-carbon double bond. A typical example of that is propylene. We have a propylene monomer here, which is CH2, and you have a double bond here. This reaction, the double bond undergo polymerization to form a single bond, and that is why it is called chain growth polymerization. So why do we call it chain growth polymerization? When you look at it, you have, for example, the polymerization will start by the first monomer, and the second monomer will add to that to become a dimer, and another monomer will link to this to become a trimer, and then this reaction continues to have a tetramer, you have a pentamer, you have hexamer, and you have what? Heptamer. But this reaction continues until all the monomers are consumed. So what you see here is this one continues a very long chain. For example, if n is 100, it means you are going to write this unit 100 times. But generally, this is represented in a simplest form, represented in a short form, where you write this repeating unit, the unit that is repeated, and then you put what? The bracket. For example, here I have 1, 2, 3, 4, 5, 6, 7 units repeated. So n here become what? 7. And you remember in chapter 4, we discussed about the chemical structures of polymers. That is, polymers are usually represented in form of a unit inside the bracket, and this unit is called repeating unit. The number of repeating unit is called the degree of polymerization. This is already we covered in chapter 4. But the most important thing here is the monomers are adding to the chain to form a long chain molecule, and that is why it is called addition polymerization, or otherwise called chain growth polymerization. Now, this Free radical addition polymerization usually takes place in 3 different steps, because the polymerization doesn't just take place automatically. It happens in 3 different steps. The first step is called initiation. Initiation means the beginning of the polymerization, and then you have propagation, which means the continuation of the polymerization, and then this will not continue forever. It will come to an end, and that end is called what? Termination, end of polymerization. Now, if you look at how does the polymerization start? In the industry, once you put the monomer in a reactor, the monomer cannot react by itself. It needs a chemical called initiator to start polymerization, especially for free radical polymerization. But if we are talking about coordination polymerization, then we'll be talking about the catalyst to start the polymerization. So what happens is the initiator at high temperature will undergo what we call homolytic cleavage. And you remember in chapter 1, we discussed about different ways covalent bonds can be broken. We have what we call homolytic cleavage, which will produce free radicals, and then we have heterolytic cleavage, which will produce a cation and an anion. But here what we have is homolysis, that is, the initiator will break into what we call a free radical. Now this free radical is represented with what? R dot. And you remember we said a free radical is an atom or a group of atoms that has 1 free electron. But if it has plus, then it is called a cation, and if it has minus, then it is called an anion. So the initiator decomposes to give a free radical. Now the free radical, which is R dot, will react with the monomer to give microradical, that is Rm dot. So here you have a free radical reacting with the monomer to give Rm dot. These 2 steps are called initiation. These 2 steps are called initiation. Now this macroradical will react with another monomer to become a dimer with free radical. So you have Rm plus M will give you RMM dot. This continues. Another monomer adds to that, becomes what? Trimer, RMM dot, and then it continues. RMM dot gives what? RMMM dot. This chain addition of monomer to the chain growth continue until all the monomers are consumed, and all these steps are called propagation steps. And when you look at the propagation steps, you have a free radical reacting with a neutral monomer to give what? Another free radical. Now, the last step is called termination, where the free radical are consumed. Because once you have RMM dots, which are represented as a long chain with RMMM dot here, with another one electron from here, 1 electron will combine together to form what? A bond. So this bond will end up with a polymer chain without free radical. So termination involves reaction of micro free radical to give a neutral polymer, which we call sometimes a dead polymer because it is no more active. So these 3 steps are called free radical addition polymerization. We call it free radical addition polymerization because the reaction is initiated by a free radical, propagated by a free radical. So free radical addition polymerization is addition polymerization that is initiated and propagated by a free radical. But if the polymerization is initiated by a cation, then it is called cationic addition polymerization. If it is initiated by an anion and propagated by an anion, then it is called anionic addition polymerization. The steps are the same. The only difference is here we have a free radical In cationic polymerization, we have a cation, and in ionic polymerization, we have what? An anion. Now, let's look at, and this is what I've said before, the definition of a polymerization that is initiated, which means that is started and propagated, means continue by a free radical, that is called free radical addition polymerization. Now, let's look at a typical example here. We have a monomer. Here I have X. X could be hydrogen. If X is hydrogen, then we say it is what? Ethylene. If X is CH3, then it is propylene. If X is benzene, then it is styrene. If X is Cl, it is vinyl chloride. All these behave in a similar way. But what you have here, you have the monomer, irrespective of what the monomer is, because the reaction takes place on the carbon-carbon double bond, and that is why it is called addition polymerization. So you have a free radical initiator, and then you end up with what? A polymer. And this polymerization is used to produce mainly, for example, in Saudi Arabia, one of the SABIC affiliates, they produce low-density polyethylene using a free radical polymerization. And at the same time, the polyvinyl chloride, which is produced in either petrochemia or chemia, I'm not very sure, it is also based on free radical addition polymerization. Now, what is this initiator? Initiator is a molecule that starts or initiates the polymerization. And the common free radical initiator, we have a lot of them, but the common ones are, I've given you 4 examples of common free radical initiator. We have the benzoyl peroxide. The benzoyl peroxide will break at the oxygen-oxygen bond to give a free radical. You have AIBN, which is iso-bis isobutylnitrile, will also break at 2 points, here at this point and at this point, to generate a free radical and a nitrogen. And then we have tertiary peroxide, which behave like a benzoyl peroxide, in which the oxygen-oxygen bond is broken to give a free radical. And in the case of tertiary butyl hydroxide, it also breaks at oxygen-oxygen bond to give hydroxyl free radical and also another free radical. These are the most common free radical initiator. For example, this one, you are going to use this one in the lab during your experiment for the production of polystyrene. And also this one, you are going to also use this in the lab during the experiment where in the production of I cannot remember the experiment exactly. I think is polyacrylonitrile. I think experiment number 9 or 10, I'm not very sure. And then some of these free radicals will be used in the next level during your class in industrial polymerization. So these are different, the common free radical initiators, but of course in the industry, they have different types of initiator depending on the type of material that they are going to produce. So here we have a monomer will undergo free radical addition polymerization to give a polymer. Example of this initiator, free radical initiator, include this. You can use this to produce a polymer, you can use this to produce a polymer, you can use this or any of these free radical initiator. But of course, all this becomes free radical, decomposes into free radical when you apply at high temperature. Now let's look at a typical example of polymerization of polyvinyl chloride. Polyvinyl chloride is one of the polymers that is produced in petrochemia, in which vinyl chloride monomer is converted into a polymer called polyvinyl chloride. Polyvinyl chloride is used in a lot of applications like conduit, in pipes, water pipes, and different applications. So the polyvinyl chloride also the polymerization also happen in 3 different steps: initiation, propagation, and termination. Now, when you look at this here, we take example of AIBN, isobutynitrile, which decomposes into nitrogen and a free radical. Now, this is a free radical, which is represented as what? R dot. This R dot will react with the monomer to start the polymerization, to initiate the polymerization, to form another free radical. So these 2 steps are called initiation. Now, once the polymerization starts, it continues by the macro free radical. This free radical that is generated during the initiation step combines with another monomer, vinyl chloride monomer, to form a dimer. Now, this continues until it becomes trimer, tetramer, pentamer, hexamer, and then it continues until you have a long chain, which is represented as what? As this. Here, X could be 100, it could be 100,000, it could be any number, very large number. So once you have these micro free radicals, that is free radical, that long chain molecule with a free radical, they can now combine together in a step called termination. Now, when you look at this, this is a micro free radical because during initiation, different chains of the polymers will be initiated, and then the monomers will add to the chain to become a long chain macro free radical. That is macro free radicals that has a long chain with a free radical. Now, this macro free radical at the end will combine together. You see, when you look at these steps, you are still generating an active, because free radicals are very reactive. So once they are generated, they continue to react. But at the termination stage, the macrophile radical from one chain and another macrophile radical from another chain will combine together to form a dead polymer, a polymer without free radical. We call it dead polymer, or we said it is inactive polymer. So at this point, there are no more further reaction because the active agent, which is the free radical, is consumed at the termination step. So what you have at the termination steps, you have free radical plus another free radical will give you a polymer. So this is a typical example of 3 steps of free radical addition polymerization, which include initiation, propagation, and termination. Now here, termination, we have several types of termination, but for the sake of time, we may not be able to go into that because we have termination by chain transfer, we have termination by coupling, we have different types of termination. But the simplest form of termination is combination. Combination means you combine 2 free radicals into a polymer chain. Now, we discuss about free radical addition polymerization, and you remember we say free radical addition polymerization is a polymerization that is initiated and propagated by a free radical. And this free radical addition polymerization usually consists of 3 steps: initiation, which means the beginning of polymerization; propagation, which means continuation of the polymerization; and then the last one is termination, which is the end of the polymerization. So one important thing about the polymer chemist is you want to calculate what will be the amount of the initiator that you will use to produce certain amount of a polymer. For example, you want to produce 1 ton of a polymer. What is going to be the amount of monomers that you are going to, the amount of monomers, and what is going to be the amount of initiator? So the numerical problem in page 62 of your course material, CHM 155, is given here. The question says, calculate the amount of benzoyl peroxide initiator, that is, the initiator is benzoyl peroxide, required to produce 1 kg of polyethylene with an average molecular weight of 200,000, because this depends on molecular weight, assuming that 20% of the initiator is actually effective and that all termination occurs by combination. So this reaction, this information is represented in form, we have ethylene, and the initiator for this polymerization is benzoyl peroxide, which is C14H10O or O4. That is if you look at our previous slides, here, where this is benzoyl peroxide. This is benzoyl peroxide. So benzoyl peroxide decomposes to give what? A free radical that will initiate a polymerization. So the question is, we want to calculate the amount of this required to produce 1 kg. So if you look at this, the initiator is given, the amount of polymer that will be produced is given, which is 1,000 grams, 1 kg, and the molecular weight of the polymer is also given, which is 200,000, and then here we have the efficiency of the initiator, which is what? 20%. So to calculate the amount of benzoyl peroxide, what we need to do is to first to calculate the degree of polymerization. We calculate degree of polymerization, and then from there we calculate the number of ethylene monomers. Then we use the number of ethylene monomers to know the number of chain. Then when we get the number of chains in the polymer, the number of chains is equal to the amount of benzoyl peroxide, but this amount needs to be converted into a mass, because the question says calculate the amount. Here we're talking about what? Grams. So the first thing is to calculate degree of polymerization. And you remember in chapter 4 we discussed, we've learned how to calculate degree of polymerization. Degree of polymerization is the molecular weight of the polymer divided by the molecular weight of the repeating unit. Remember, repeating unit is what is inside what? The bracket. So if you look at this, the repeating unit is C2, 2 carbon and 4 hydrogen. So carbon is equals to 12 and hydrogen is equals to 1. So when you multiply 2 by 4 and 4 by 1, we end up with 28. So the molecular weight of the repeating unit is 28 gram per mole. So if we want to calculate degree of polymerization, we take the molecular weight of the polymer, which is given from the question, we divide it by the molecular weight of the repeating unit. That will give us what? The ethylene units in the chain, which means that for each chain of the polymer, each chain has 7,143 ethylene. Now we want to calculate the number of chains. Now to calculate the number of chains, we need to convert the polyethylene into number using Avogadro's constant. So what we do here, and we remember in general chemistry, we say 1 mole of a substance contains 6.02 times 10 to the power 23 mole Avogadros per mole of Avogadro. So here, what we have, we take the number of ethylene, the mass of ethylene, which is 1,000 grams. So we convert this kg into grams. So we take the number, which is 1,000 grams, divide by 28, which is the molecular weight of ethylene, multiplied by the Avogadro's constants, which said in general chemistry, we say 1 mole of any substance contain this number of what? Units, 6.02 times 10 to the power 3. So we multiply the moles by 6.03. So mole is mass over the molar mass. So mass is the mass that is given here. We change it to grams, divided by 28, which is the molar mass of ethylene, to give multiply by this, so we have this number of ethylene units. So if we have this number of ethylene units, from here we can calculate the number of chain. For example, if I have 200 students in my class and I want them to form a chain, and each chain must contain 20 students. So the number of chains that I will have, the number of lines that I will get at the end of the day will be 200 divided by 20, which is 10. So basically, here we want to determine the number of chain of the polymer. So the total number of monomer is 215 times 10 raised to the power 23, and each chain has 7143. So we divide this number by this to get the number of chain. So the number of chain is the number of ethylene divided by the degree of polymerization, and once we do this, we get 3 times 10 raised to the power 21 chains. Now for each chain is initiated by initiator. So at the polymerization, each chain, at the beginning of each chain, you are going to have an initiator. So the number of chain is equal to the number of initiator. So if we multiply by, if we take the number of chains, which is this one, multiply by the molecular weight of the initiator, that will give you the number of the amount of the initiator in gram per mole. So how do we get this the molar mass of the initiator? We use this the chemical composition C14 H10 O14 to calculate the molecular weight of the initiator. So this number multiplied by the number of chain will give us the amount, but the amount we are going to get is going to be in grams per mole. So to change it to mass, we divide by Avogadro. So Avogadro is per mole we cancel per mole, we end up with what? Grams. Sorry, this is a mistake here. This is supposed to be 1.206 grams. So please take this one out. So at the end, the amount of initiator required is 1.20 gram if all the initiator are effective. But the question says only 20% of the initiator is effective. So in this case, we have to take more. More amount of the monomer. Instead of 1.2, we end up taking more. So what do we do? How do we convert that? Since only 20% of the initiator is efficient, the amount of initiator will be 100 divided by 20 multiplied by 1.2, and that will give us what? 6.03 grams. So 6.03 grams is the amount of initiator that will be used to produce 1 kg of polyethylene, assuming that only 20% of the initiator is what? Effective. So 20% of 6.03 will give you what? 1.20. But if all the initiators are effective, then we don't need to carry out additional calculation to determine the exact amount of the initiator. So basically, in this question you are required to calculate the mass of initiator required to produce certain amounts of the polymer using a particular initiator. So the first thing, and the molecular weight of the polymer is given. So the first thing we need to do is to determine the degree of polymerization. Degree of polymerization is the molecular weight of the polymer divided by molecular weight of the repeating unit. Then from there, we take the mass of the polymer and convert it to what? Number, because we want to know the number of units. Now, the degree of polymerization tells us the number of units in one single chain, but we want to calculate the total amount of the monomer. So we take the mass of the polymer divided by molar mass of the polymer, the molecular weight of its repeating unit, that will become a mole. That mole is then multiplied by Avogadro's constant, and this will give you the total number of the monomer. The total number of monomer divided by the degree of polymerization, that will give you the number of chain. The number of chain multiplied by the molecular weight of the initiator divided by the Avogadro's will give you the amount of initiator in grams. Now, if all the initiators are effective, then that is the end. But if some initiators are not effective, then we have to calculate the amount. We have to put that into consideration by calculating the required amount of the polymer, the initiator required for the polymerization. So this brings us to the end of the numerical problem in page 52. So we move to the next concept under free radical addition polymerization, which is a chain transfer reaction. Chain transfer reaction is a reaction that is very common and in addition polymerization, and it is also used to produce controlled molecular weight of polymer. Especially if you want to produce different batches of polymers, then you have to use what we call chain transfer reaction. Now, chain transfer reaction, by definition, is the transfer of free radical on the growing chain to another molecule. So if you have a growing chain here, this is a growing chain with a free radical, and then you transfer the free radical to another molecule. Here we call it what? Chain transfer agent. Then you end up with a polymer without a free radical, and then the free radical is transferred to another molecule to initiate, to start another chain. So here you end up with a smaller molecular weight of the polymer. And when you look at in the industry, for example, if you are producing polyethylene, usually they add hydrogen to control the molecular weight, and this happens by a reaction called chain transfer reaction. The more you put the hydrogen, the lower the molecular weight you will get as the final product. So this transfer agent could be a monomer, or it could be initiator, but this is not very common because the amount of initiator is very small, or it could be a solvent if you are talking about solution polymerization, or it could be a dead polymer, a polymer that has already terminated, inactive polymer, or a transfer agent. Sometimes you need to add a transfer agent into the reactor to control the molecular weight. So all these processes, this process is called chain transfer reaction, and as I said here, chain transfer could be transferred to a monomer, it could be initiator, it could be solvent, dead polymer, and a transfer agent. Now, for the sake of, because of time, we are going to discuss only two examples, that is chain transfer to the monomer and a solvent, which are very common. So when you look at this here, for example, we have a growing chain, it has a free radical, and this is a monomer. Now, instead of adding this monomer adding to this chain to become longer, the free radical, this free radical is moved to this monomer, and then to complete the valency of hydrogen, to complete the valency of carbon, the hydrogen will move to this carbon so that it becomes tetravalent. You remember we said in chapter 1 that the valency of carbon should always be what? 4. So this reaction is called what? Chain transfer. So you move this free radical here, and then you move hydrogen from here to this growing chain. So this reaction is called chain transfer. Sorry, there's supposed to be a free radical here, there's supposed to be a free radical here, and this free radical will now initiate another polymerization. But it is important to mention that here, chain transfer reaction to a monomer is competing. It's a competing reaction with what? propagation. You remember we talked about 3 steps in addition polymerization: initiation, propagation, and termination. So if you have a chain transfer, if you have a monomer, you have a growing chain reacting with a monomer, reaction can either be a chain transfer or propagation. If the monomer add to the chain, for example, this is 1 monomer and you add, it becomes 2, so the chain increase, the chain length increase, then it is called what? Propagation. But if the free radical from this is transferred to give this, which means that the monomer is not adding to it, but just free radical is being transferred, then it is called chain transfer reaction. So you need to know the difference between these 2 types of reaction, because sometimes you are going to be given this one and growing radical with a monomer, and then the product will depend on what is here. If it is chain transfer, it means there's going to be transfer of free radical. If it is propagation, it means that this one will add to the chain to increase the length of the chain. So you should not be confused. You shouldn't confuse these two terminologies: chain transfer and propagation. Chain transfer is transfer of free radical. Propagation is addition of the monomer to increase the length of the polymer. So another example of chain transfer reaction is chain transfer to a solvent. Now, chain transfer to a solvent is you have a growing chain like this one, but you have a solvent. And a typical example here, the simplest solvent I use is water. Now, the free radical here will move to the oxygen, and hydrogen from water will come here, so you end up with what? OH free radical, and then you end up with what? A dead polymer. So this one is a monomer, and this one is what? A solvent. So chain transfer to a monomer means that the free radical is transferred to a monomer. Chain transfer to a solvent, it means that the free radical is transferred to a solvent, depending on the type of polymerization. For example, in solution polymerization, you end up with a free chain transfer to a solvent. So as I mentioned earlier, we have several examples, but for the sake of time, we are going to limit ourselves to 2 examples: chain transfer to monomer and chain transfer to solvent. And generally, chain transfer to polymer can lead to formation of what? Short branching. So when you do a chain transfer to polymer, of course, that's another one. When transfer to a polymer, it can lead to creating a short branch at the backbone of the polymer. So the last concept we are going to look at under this under chapter 5 is what we call inhibition and retardation. Inhibition and retardation. And generally, these ones are usually measured in terms of conversion time. When you start a polymerization, conversion means the amount of monomer that has changed into a polymer, and as a function of time. Now, at the beginning, if you have a monomer in a container or in a reactor, no polymerization, it means conversion is what? 0. That is, no monomer is converted into a polymer. But after some time, maybe 13% of the monomer will react to form a chain. For example, if you have 100 units of monomer in a reactor and 20 of them undergo reaction, it means that the conversion is what? 20%. That is 20 out of 100. So this concept here, we have inhibition and retardation. Generally, when we talk about inhibition means inhibitor is a chemical that stops polymerization completely, and retardation is a compound or a molecule that will slow down the rate of polymerization. And generally, these concepts are very important. For example, if you want to transport styrene monomers are very reactive. And if you transport them in a container, it's possible that they can undergo autopolymerization. That means that they can polymerize inside the container, and then they produce, and you know, the polymerization reaction is exothermic reaction, which means that it generates heat. So it will lead to an increase in temperature, and this increase in temperature will lead to a pressure build-up in the container, which can lead to explosion. So that is why, according to Department of Transportation, United States Department of Transportation, which we usually DOT, prohibit transportation of styrene monomer without inhibitor, because inhibitor usually will stop the polymerization during the transportation process, such that unexpected polymerization will not happen. So this is very important when it comes to transportation of the monomers. Some monomers are very reactive, and you have to add inhibitors. And in one of the experiments, you are going to produce polystyrene. The polystyrene you are going to use is also inhibited, because if you keep it for some time, it will undergo polymerization. So before you can start that experiment, you are going to remove the inhibitor, because the inhibitor will stop you from carrying out the experiment. So part of the experiment is to prepare sodium hydroxide solution, which is used to remove the inhibitor. So this experiment, you are going to do that. We are going to do that in one of the experiments, inshallah. But what here, generally, we have, depending on the conversion with time, we have different types of polymerization. For example, if the polymerization take place normally, it means that as the time increases, the monomers are converting into polymer. Then that is called what? Normal polymerization. But if the conversion is not increasing at the same rate the time is increasing, you see, if you have here, at this time, the conversion is low compared to this one, it means that this polymerization is slow, and this polymerization is called what? Retardation. And then the last one, which is called inhibition. Inhibition, here you have no polymerizations for almost for a certain period of time. From this time, for example, if this is 10 seconds, 20 seconds, 30 seconds, 40 seconds, 50 seconds, no polymerization. And then after that, then polymerization becomes what? Normal. It goes in the same direction as normal polymerization, and this is called inhibition. The period, this point where there is no polymerization, this time period where there is no polymerization is called induction period. So it means that the polymerization will start only after certain period of time, and that period of time is called induction period. But once the induction period is over, then the polymerization will start in a normal fashion. But in the case of retardation, the polymerization starts from the beginning, but it is very slow. So retardation means slow polymerization, so that is why we have retarder to slow down the polymerization. Inhibitor means stop polymerization completely, and then we have the normal polymerization. Both degree and rate of polymerization can be controlled by the use of the substance known as retarder and inhibitor. These processes are very important when you want to stop polymerization, because polymerization is only beneficial when it happens in a reactor. If you are conveying a monomer in a pipe into a reactor and polymerization takes place at that point, it will lead to a solid, and that solid can block the pipe or the valve. So that is why at that point you need to add what we call a retarder, which will slow down the rate of polymerization, or inhibitor, which will stop the polymerization completely until the monomer gets into the reactor where polymerization is required. This process is usually limited for monomers that are very reactive, like polystyrene and other polymers, other monomers, and that is why these monomers cannot be stored or transported without inhibitor, and this is because of safety consideration, because the monomers can react with each other to generate an heat, which, because it's an exothermic process, and that heat that is generated can lead to what we call pressure buildup in a container, and that container can explode, which will lead to uncontrolled release of monomers, and most of the monomers are very toxic. And this brings us to the end of this chapter, and if you have any question, please feel free to post your questions on the Blackboard. You have the discussion forum. Post your questions on the discussion forum, and I encourage other students to answer those questions. I'm going to log in to moderate to give you the correct answers to some of the questions that have been posted there. And if you still have additional questions, you can also send me an email. But I strongly recommend that we should use the Blackboard for the benefit of other students, so that once you ask general questions, other students can answer, and I can also provide you with the correct answers, which will be beneficial to everyone. Thank you very much, and hopefully, inshallah, I will prepare the next chapter, which is chapter 8, condensation polymerization, because chapter 7, which is ionic polymerization, is divided into cationic and anionic, and these polymerization processes are similar to free radical polymerization. The only difference is the free radical. Here you are using a free radical, there you are using an anion or a cation, but the polymerization steps are very similar, which means that you have initiation, propagation, and termination. So for the sake of time, we are going to move to the next chapter, which is chapter 8, which is condensation polymerization. That is polymerization that involves reaction of functional group. Thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh.